In this experiment, you will synthesize quantum dots comprised of cadmium and selenium. You will isolate a sufficient quantity of cadmium selenide quantum dots to analyze them using UV spectroscopy. You will literally see how varying a single reaction condition impacts the size of quantum dot produced and determines the trend between molecular size and physical properties using spectroscopic measurements. Nanotechnology deals with very small particle sizes of substances, typically 100 nanometer or less. By comparison, the width of a DNA molecule is approximately 2.5 nanometer. The properties of these substances are closely associated with their size. This variation of properties with size is not observed in the macro-sized form of these substances. These compounds are typically semiconductors, which are solids whose conductivity can be manipulated either by addition of impurities or a change in temperature. Atomic orbitals on individual atoms interact to form molecular orbitals in a substance. The number of unoccupied and occupied MOs is the same as the number of interacting atomic orbitals and increases with the number of atoms in the solid. The illustration here uses the 2s orbital on lithium. As the number of lithium atoms increases in the crystal, the increase in 2s orbitals causes a corresponding increase in molecular orbitals. These MOs are delocalized over all the contributing lithium atoms. As the number of MOs increases, the energy separating them gets smaller. Eventually, the MOs in the occupied orbitals, as well as the orbitals in the unoccupied ones, are so close in energy that each is referred to as a band. The occupied orbitals are called the valence band, and the unoccupied ones the conduction band. The energy separating the highest valence MO from the lowest conduction MO is called the band gap. The band gap is responsible for the conductivity and light properties of quantum dots, and manipulating it experimentally allows a substance of desired properties to be designed. The wavelength of emitted light is dependent upon the band gap. The color of quantum dots is an indication of the energy of separation between the valence and conduction bands. The band gap is a function of particle size. As the size of the quantum dot gets larger, the energy separating the MOs decreases and the band gap energy decreases, or displays a red shift. As the size of the quantum dot gets smaller, the MO separation with a band increases and the band gap also increases, or shows a blue shift. The energy of the photon needed to excite an electron from the valence to the conduction band gets larger as the quantum dot size gets smaller. Substances are grouped into three general categories based on the size of the band gap. Those substances with overlapping conduction and valence bands, in other words, no band gap, are classified as metals. A zero band gap makes empty orbitals in the conduction band readily available to valence electrons and explains the high conductivity of metals. Semiconductors have a small band gap and are typically used to control current flow in one direction. Silicon is a typical semiconductor whose electrical properties are controlled by the addition of small amounts of contaminants from either group 13 or group 15 in the periodic table. Insulators have large band gaps, making it difficult for valence electrons to be excited into the conduction band. Typical insulators are glass, porcelain, or composite polymers. The movement of an electron from the valence band to the conduction band results in the creation of an electron-hole pair. The electron can be excited either by heat or light. The electron pair hole can be destroyed when the electron returns from the conduction to the valence band. The hole created in the valence band is not a positive particle, but the absence of a negatively charged electron. The excited electron is now available to contribute to the electrical current and is delocalized throughout the crystal lattice. Also, the holes in the valence band will now allow movement of electrons in the valence band, which effectively moves the hole, and this also contributes to the electrical current. This reaction is completed at a relatively high temperature. The high boiling solvent used is 1-octadecene. Cadmium is added to the reaction mixture in the form of cadmium oxide and is needed for the core of the quantum dot. Oleic acid, a long-chain fatty acid, is used to complex with the cadmium cation, helping to solubilize this cation in the organic reaction mixture. Trioctylphosphine selenium, or TOPSY, serves a twofold purpose: adding selenium, which is required for the core of the quantum dot, and providing trioctylphosphine, which is needed to form the stabilizing outer layer. Reaction time is the parameter which is manipulated to affect the size of the quantum dot. Aliquots of the reaction mixture are systematically removed at set time intervals, which effectively quenches the reaction in an attempt to control quantum dot size. Interestingly, the chemical composition of the particle does not impact the visible or fluorescent appearance of the quantum dot. The particle size, however, does have an effect on the appearance. The major goal of this experiment is to synthesize monodisperse quantum dots, that is, particles that are relatively small, 100 nanometer or less, and uniform in size. Quantum dots differing in size by only a few nanometer will have their lambda max in the visible spectrum differ by only a few nanometer. In other words, close but clearly not the same. Factors affecting the size of the quantum dots are concentration of the reactants, the temperature of the reaction, the time the quantum dot is allowed to grow, and the surfactants used. The effect of particle size of the quantum dot on the physical property of color is apparent in both room light and ultraviolet light. A handheld ultraviolet light source will be provided in lab to see the visual effect of ultraviolet light on a series of quantum dots produced in this experiment. The visible spectrum of each batch of quantum dots will be recorded using the lab's UV-Vis spectrophotometer. This experiment is completed in pairs. The slowest step for this experiment is getting the sand bath heated to the specified temperature. This should be started immediately at the beginning of the lab period. The timer on the centrifuge is not very accurate. You'll need the timer in your cell phone or use the lab's wall clock. If the pellet formed by centrifugation does not readily dissolve in toluene, you will have to use a glass pipette to mix the toluene and pellet by drawing the toluene up and down to dissolve the pellet. When completing the UV-Vis scan, overlay the spectrum of each sample on the same graph, with lambda max labeled for each spectrum.